We've defined electric field strength as the amount of force acting on a coulomb of charge, force per coulomb, so newtons per coulomb, right? Now in this video, we will look at a new way of defining electric field strength in terms of potential difference. So let's start by something that we already know. Let's use this definition. So let's take an example. Imagine we have a uniform electric field towards the right, created by some sheet of charge, let's say. And let's say that the strength is 100 newtons per coulomb. Let's start by asking ourselves, what is the meaning of this statement according to this definition? Well, it basically means that if I keep a coulomb of charge in that electric field anywhere, it's uniform, then that coulomb would experience 100 newtons of force, 100 newtons per coulomb. Similarly, what would it mean if I had, let's say, another electric field, say upwards, and let's say this electric field was 500 newtons per coulomb. What would be the meaning of that? Well, this would mean over here, if I now bring that 1 coulomb of charge and keep it over here, then that coulomb would experience 500 newtons of force, 500 newtons per coulomb. Okay, now let's think of this in a different way. And for that, here's my question to you. Imagine I let go of this charge. So I keep my charge over here. I'm holding it right now. Let's say I let go of that charge. What's going to happen? Well, it's experiencing a force towards the right, and so it'll accelerate towards the right. And as it does that, it's going to gain speed. It's going to gain kinetic energy as it goes towards the right, which means it's going to lose potential energy. It's just like a ball falling down. As it gains speed, it loses potential energy, right? So that means as it goes forward, it gains kinetic energy, it loses potential energy. What I want you to try and figure out is how much potential energy this coulomb of charge would have lost if it went forward, or when it goes forward, by exactly 1 meter. So can you pause and calculate how much potential energy it would lose by the time it would have traveled exactly 1 meter? So can you pause and try and figure this out? All right, let's see. So let's start by asking ourselves, how do we calculate how much potential energy is lost or gained? Well, that is calculated by the work done. The potential energy lost or gained is the work done by the electric field. And so how much is the work done over here? So the work done over here, let me write that somewhere here. So the work done over here is force into displacement, 100 into 1, that's 100 joules. 100 joules, and that work is done for 1 coulomb of charge. So work done is 100 joules per coulomb. And that means this coulomb will lose 100 joules of potential energy by the time it travels 1 meter. Does that make sense? And all of that 100 joules will get converted into kinetic energy. Another way of saying that is we can say, as I go forward by 1 meter, we will lose 100 joules per coulomb, 100 joules of potential energy per coulomb, meaning 100 volts. Joules per coulomb is also called volts. So let me erase that and let me write this as volts. 100 volts as I go forward 1 meter. So I could say 100 volts per meter. Does that make sense? Think about it. For every meter that I travel forward, I would lose 100 volts of potential in this electric field. Okay, now similarly, what can you say about this electric field? How many volts would we lose if you go 1 meter forward? All right, well, the calculation will be very similar. If I go 1 meter forward, so let's say this is 1 meter, the work done by the electric field would be 500 joules. So 500 joules per coulomb. So 500 volts for every meter you go forward. So in this electric field, we will lose 500 volts, much higher, 500 volts per meter. And this is our new way or new definition of our electric field strength. So our electric field, this number is telling us how much potential gets dropped for every meter you go forward along the field. Okay, and so now let me move this a little down. Okay, let me move this over here. All right, so now we can also say that this electric field equals 100. Instead of calling it newtons per coulomb, I can also say volt, 100 volt per meter. And what does it mean when I say electric field is 100 volt per meter? It's saying that in this field, for every meter you go forward, you lose 100 volts. Similarly, I can now write this as 500 volt per meter. Although there is a volt over here, this is not potential, this is field, volt per meter. And what is this saying? This is saying, oh, this is a much stronger field. For every meter you go forward, you lose 500 volts of potential. So what's our new way of defining electric field strength? We can say it is a measure of how much potential drops per meter as you go forward in the electric field. Okay, and how do we write that mathematically? So let me write that over here. How do we write this mathematically? We could say electric field equals potential drop, which we can write as delta V, per meter, which we can write as per distance. So per delta R or delta X, whatever you want to call that. Delta R or delta X. And what's the unit? It's volts per meter. So a new way of looking at electric field. Now, one thing we need to be very careful, this is not complete equation yet. One thing to be careful is, remember, the number is saying how much potential you're losing as you go forward. Remember, it's a drop, okay? And how do we take care of that in the mathematics? Mathematically, when we write it, if I just write delta V, it represents how much potential is gained because it's a positive number. But we are saying it's how much potential is lost. And it's for that reason we put a negative sign over here. So the negative sign is basically saying it's a measure of how much the potential drops. Think of it this way. If your electric field, let's say, is positive, let's say right side is positive. If your electric field was positive, and let's say you also move in the positive direction, delta R is also positive, what would happen to your potential? Would you gain or would you lose? You're losing. That's what we're saying, right? You're losing. And therefore, this needs to be negative. So it's saying that if both these are positive, then delta V has to be negative. And therefore, that's why we have a negative sign. And of course, in a future video, we'll solve some numericals and this will make more sense. But long story short, electric field is a measure of how much potential gets lost for every meter you go forward. Now, before we conclude, there's one last thing I want to mention of how do we write this, how do we say this technically? So whenever you're calculating how much something is changing with respect to distance, or how much something is changing per meter, we give it a name, we call that a gradient. So let me write that. This is called gradient, okay? So if I said something like temperature gradient, it means it's a measure of how much temperature is changing for every meter you go forward. So this is potential gradient because it's a measure of how much potential is changing for every meter you go forward. So our right-hand side is potential gradient. Let me shift this, sorry, there's a little space. So let me try and make this. So this, whatever we're writing, whatever we're calculating is potential gradient. Potential gradient. And therefore we can now say that electric field, this is what you will see in your textbooks, electric field is the negative potential gradient. If I just say potential gradient, it means how much it's increasing. So I have to say how much it's decreasing, how much potential is decreasing. And so we can now say electric field is a negative potential gradient. Sounds very cool to say that, but hopefully now this makes a lot of sense. Basically means how much potential is losing for every meter you go forward.